Western film university
Thank you, Mr. Chairman. I've since moved on and graduated, and I'm now currently at the University of Hong Kong. So is my supervisor. So good afternoon. Thank you for staying to the end. Today I will be presenting the thermoresistive characteristics of sintered gold nanoparticle microstructures deposited via inkjet printing from metal organic gold nanoparticle inks and sintered in air. This was part of my PhD dissertation work and is part of our ongoing effort to develop the microfabrication technologies using inkjet printing towards advanced microsensing and actuation applications. Now, to compare this with conventional microfabrication shown on the left, traditionally with subtractive, or you can refer to as subtractive microfabrication, for each device layer, the entire substrate is coated with the material, and then a lithography mask is placed on top to protect a portion. The unwanted material is etched away, and then the mask is removed before proceeding to the next step. With inkjet printing-based microfabrication, a liquid precursor material, or ink, is selectively patterned onto a surface, and after deposition, then typically some post-processing is required, in our case thermally, to render the precursor to its final form. And then this obviously requires different deposition and precursor materials. So this fabrication technology is made possible through several enabling technologies, including advanced robotic motion control, high-resolution inkjet deposition heads, and novel nanoscale materials to act as the precursors. This technology also offers several exciting possible new capabilities over other fabrication techniques, including the ability to do mass-free fabrication. Precursors can often be processed at low temperatures, enabling the use of polymeric and other non-traditional substrates, which can further lower costs. As well as the field of print electronics matures, there will undoubtedly be a need for compatible sensors and actuators to enable more complex products. But as I've said, as we're using new precursor materials, understanding the characteristics of the resulting films is important for device design. Just to introduce our ink, we synthesized in-house a metal organic gold nanoparticle ink based on some work originally developed at UC Berkeley for print electronics. It consists of a 2 to 5 nanometer gold core with a self-assembled hexanethiol shell. This monolayer is used to enable the nanoparticles to be suspended in solution to form a stable ink. An interesting property of these inks or these nanoparticles is that the small size and large surface area enable the nanoparticles to begin to sinter together well below the bulk melting point of gold. Understanding the thermal processing is then important for our steps. And as you can see here, first we deposit the ink and solvent on a heated substrate to rapidly evaporate away that carrier solvent. At which point then we can ramp the temperature of the substrate, at which point then the organics begin to break down and will sublime away or sublimate away, and then the nanoparticles will begin to sinter together and ideally form a coherent gold structure. Understanding this process and the resulting films is of study here. And there are two ways to actually monitor this process. One is visually. The ink goes from a black organic to a gold color, or alchemy as mother refers to it. Or alternatively, you can monitor this process by watching the resistivity of the films during sintering. However, monitoring this resistivity poses some challenges, and 4-point or Kelvin resistance measurements are commonly employed in the microelectronics industry for standard films, and this typically uses a collinear 4-point probe, which is readily placed on the large area wafers. Unfortunately, for our processes, we are only placing material in small sections, so that would make alignment difficult, as well as we're starting with an organic film, contacting them directly would be a challenge. Fortunately, Enderling et al. Has put forth a linear bridge structure, which allows for the simple measurement of the sheet resistance of a bridge if the length and width are known. using this relation here. And then if you also know the thickness, you can then back out the resistivity. For our work, then, we wanted to extend this to allow the use of this kind of structure for the measurement of inkjet printed films. And so we've developed a test structure, which I'll detail the fabrication in a moment, to use this form of measurement for our work. To do this, we start with any substrate. In this case, a clean Corning 0215 soda lime glass slide. We then use a polyimide shadow mask that's laser cut to define the shape of our pads with a gap. A 250 nanometer gold layer is then sputtered onto the surface, and this is kept thin in order to minimize the effects of stepping across with our inkjet printed films. Silver epoxy is then applied to the pads to enhance probing robustness, and then the shadow mask is removed, and the epoxy is allowed to cure. And this gives us some dimensions of our test structure using this work, where the important one here is the gap presented between our two gold lines is 900 microns. Now, we can place this on our custom inkjet printer, and we can deposit our material of interest, in this case the gold nanoparticles, orthogonally across the test structure to form a bridge. Once we've done that, then we can place this thing under measurement, and we can then interrogate the bridge. Measurements were performed, and here's a resulting structure from our work, and you can see the printed gold line here. This test setup was used then for our measurements, and a custom spring-loaded pogo pin jig was used to connect the device to the instruments. The pogo pins were used to allow secure probing as well as to allow for thermal expansion of the test setup. Additionally, a hot plate provided temperature control, a digital multimeter provided measurements, and a LabVIEW control PC provided data acquisition. As I mentioned earlier, during sintering, a large resistance drop can be observed. And just to show our test setup in action with that part of the process, these are 4 different films that were deposited in the same way. And for the first 10 minutes, they're left at a low temperature to evaporate their solvents. At the 10-minute mark, the temperatures were increased, as shown here. And after some time, a large decrease in resistance is observed as the organics break down and the nanoparticles begin to connect with one another and sinter together and conduct. After some period of time, then, the resistivity of these films becomes more stable, and we have a stable gold film, ideally. Now, with that, then, after we started this work, one thing we wanted to understand then was the temperature response of these films for a couple of reasons. One, understanding the temperature response of these films is important for device design, as sensors and other devices often undergo a variety of ambient conditions, as well as the unique properties of these films may be useful for things such as platinum, or not platinum, in this case gold, or RTDs, and flow sensors. An important measure, then, of temperature is the temperature coefficient of resistance, which is shown with this relation here. And that's what we chose to measure using our technique. For our experiment, we used the test structures outlined previously, and then gold nanoparticle bridges were deposited in the same manner on all of our test structures. After deposition, then, each bridge was underwent a different sintering temperature, either 175 or 225 C, to look at the variations. And this duration was held for 24 hours to hopefully ensure that a stable gold film was rendered before the TCR measures were performed. Each sample was then placed on a hot plate setup, and the temperature was stepped through a variety of temperatures and measured to watch the response. This was kept below 150 C as a maximum, which is below the sintering temperature, to minimize effects from that. So just to show the response of some of our samples, and you can see in red here are the various set points of our heater, and in each time it's held for 10 minutes. And you see for both of these sintered films, as it heats up, it rapidly rises and is very stable at each point, where the change is limited by the hot plate used in this experiment. Stability was also of interest, so this was repeated on multiple cycles. And if we take the same sample here, we can place the same sample on 2 different cycles, and you see that there's no appreciable drift. These films were then imaged using scanning electron microscopy. using a scanning electron microscope. And what we observed on these films was a highly porous for both cases, which was very interesting, and as I hypothesized, it's due to the poor adhesive nature between glass and gold, which is well documented. One interesting thing, though, is that this highly porous gold presents a large surface area, which has potential interesting applications for sensing. If we take our data and we average it at our 3 temperatures to compute the TCR, we find for both of our sintered films that a very linear response was observed, and we can then compute them as 2,000 or 2,300 ppm per degree C for our measured samples. This is reduced over bulk gold, which is about 3,400 ppm per degree C, but agrees well with similar films, including a low resistance sputtered gold film, as well as a discontinuous gold film reported in the literature. Now, if we assume that the film, or can just approximate the film as rather homogeneous, even though it's highly disordered, we can then back out the sheet resistance per the earlier relation as 830 or 910 milliohms per square. So with that, I'd like to thank you for your attention, and I've shown you the first measurement results of the sintered gold nanoparticle films and their TCRs, and they exhibited high stability and linearity over the measured range. A 4-point test structure was introduced and used for our experiments, and is hopefully useful for other inkjet explorations. Also, our bridges were observed to have a complex structure, which may potentially offer several interesting sensing applications where a high surface area of gold is desirable. One thing to remember about this technology is that with this technology we can deposit gold at low temperatures in atmospheric conditions on arbitrary substrates, which offers potential applications or interesting applications over conventional techniques. Thank you for your attention.